Alrighty, so now we're gonna go to the OS part. And what we tackled in the face-to-face lecture is concurrency, and we're gonna see different mechanisms and the different tools that we use to tackle concurrency. Of course, we spent some time trying to understand what concurrency is, and the best way to sell it would be when two or more processes are trying to fight over something. And one of the main resources that two or more processes might fight over is definitely the CPU, and I want to exclude the CPU from today's lecture. Right, so a couple of things. EOS manages processes and threads. This is what we've seen up until today, and from now on, whatever is true for the processes is also true for the threads. Hence, I'm gonna speak in terms of processes from now on, right? Because threads might be seen as a mini processes, or a process could be made out of multiple threads. Fair enough? So when we have multiple processes within a monocore system, in uniprocessor system, well, a technical word from now on that you should be aware of, this is what we call multi-programming. Fair enough? And another definition now that you need to be aware of, multiple processes executing now on multiple cores, like unicore here, multiple processes, and this is what we call the impression of parallelism. Here we have physically multiple cores, or even logically, it doesn't really matter, but I mean from the OS point of view, it's seeing more than one CPU, so basically this is real parallelism, and we're gonna call those multi-processing. Fair enough? And the third thing that we've seen lightly in the previous lecture was the fact that when we have a distributed computer, and this is what we call distributed processing, and we've seen it with the distributed operating system that I introduced in the very first slide of last week's lecture. Alright, so yep, so here we see a bunch. So typically in an exam you'll have a schematic, and then we're going to try and analyze it together. So here we're seeing a bunch of processes and a bunch of resources. So this is my computer, and here it feels like this is the memory, and we can see inside it the stack, and we said that the stacks are relevant to functions, and we're going to tackle those in more details in the CA course. And by the way, this is a screenshot from the CA course. We're going to see it in more details real soon. Right, so you can see that the memory has a part for instructions, and then we're gonna use some data. Some of the data is static, and then they are related to the function and to something else. Doesn't really matter for now in this course. What I want you to notice are the reserved areas. So mostly that one. Reserved for who? For what? What kind of entity should, in a memory have a reserved area? Naturally, in this course, we're gonna see the kernel, and it is the kernel. Right. So here we're seeing processes, 6 of them, and one of the questions that someone might ask is which process is currently active and running. So the sole process that is hooked to the CPU is P5, hence it's at least partially loaded in main memory, and it's connected to the CPU, so it's most likely this one that is currently running. But we can see that we have different resources here. I'm excluding the CPU and the memory, and apparently all those resources could be used by any of the processes, so it could be a source of problems. They're gonna compete, they're gonna try to fight over those resources. Right, so remember, unless I say otherwise, we are gonna consider that we always working with a single CPU. Right, so shared hardware and software resources. So the resources we can see here, the hardware ones most probably, but we can also see software resources, and we're gonna see them in a minute from now. So this is definitely a source of conflict because processes fight all of them. Alright, so let's see an example. It will be easier to understand. So we have two processes. No, not two processes. I wanted to correct it, but I forgot. So two processes, P1 and P2, right? And there's a shared resource. So a shared resource, this means that it could be a source of conflict. And one last thing that we're trying to understand here, and this is a typical case study that I might give you in an exam, that we're using 1 tick of CPU time for each process. What does this mean? Where's my pen? So 1 tick of CPU time. So the tick, we can see it for now, it's like the clock tick, so it could be seen as a unit of time, and this is the unit of time of the CPU. It doesn't really matter. This is what we're going to talk about later in the CA course. Alright, so these are the units, and apparently it's we have of course, because I didn't say otherwise, so we have a single CPU, and then we're alternating between P1 and P2 inside the CPU, and each process that gets the CPU will execute for a tick, and then it will leave and give it. So what kind of selection process happens in the ready list of the processes? So which one will go to executing based on what mechanism? So is it priority based? Doesn't seem so. Is it first in first out? Apparently not, because we're alternating between two. So most probably it's time slicing, and this is what we're gonna call it for now. So time slicing. All right. And once we kicked out a process from being, from execution back to the ready state, what do we call that transition here? It's preemption. All right. So you can see a little bit what's happening here. Alright, so let's see what is the purpose of P1 and P2. So P1 only has one thing, which is try to execute one instruction, which is a system call in that case, right? And it's trying to use the printer and to print out and wanna print out a message. And P2, same thing, however it wants to print out a different message. So let's try to imagine the scenario of execution here, considering that every time each process gets the CPU, for each tick it will be able to execute only, to print out only one character. So it's one character at a tick. Alright, so what would happen here? So we have time slicing, so P1 will execute first, then we're gonna go to P2, P3, etc., etc. Alright, and here you can notice that we're having context switching, dealing with the PCB, stuff like that. I don't care about that today. So P1, 1 tick, P2, 1 tick, 1 tick, 1 tick, and we're gonna keep on alternating. So each time I will execute one letter. I will print out one letter. So B, B, O, O, etc. And we're gonna end up with that particular message. And this is not good. This is not the bad of the printer, it's just the fact that we're using a mechanism and we're not protecting the printer, so hence we ended up with that. And today's lecture is how to deal with that situation and how to try and prevent from getting to a situation like that. Alright, so this is what we've learned. We're gonna put a technical term on it, so it's a mutual exclusion. When someone like Homer here is trying to use something, however that resource is already being used by someone else, in this case it's Marge, we can tell from the hair, so Homer is not allowed to use it. So using the processes, if P1 is using the resource, the printer in that case, right, so P2 must wait for it. So hold on for a second. So this should ring a bell. So someone was ready, went to the running state, and then is trying to use something that is not ready to be used. So we will go to the block state. See, this explains that. Now the question is, we said earlier, so in order to get out from the block state and go back to the ready state, right, something needs to tell us something else, signal us, give a signal. What would that be? So here is the infamous interrupt that we talked about. Someone will say that the printer is ready now, right? So we'll signal to B, and then B could, P2, could go from the block state to the ready state in order to be able to use the printer. So it all makes sense now. Alright, so another technical thing here. So systematically now, whenever we have a shared resource, we're gonna call it a critical resource. And I wanna use any kind of resource but the memory and the CPU, excluding the memory and the CPU. It could be a printer, a scanner, a microphone, any physical thing that could be shared between processes. Now, we've noticed that in order to use the resource, well, there was an instruction in the code. So the code portion that is meant to use the critical resource, we're going to call it a critical section, right? And hence the conclusion of that slide, that only one process at a time is allowed in its critical section. So no one will get to the print statement if, let's say, P1 is should be unable to get to the print statement if P2 is currently in its print statement. Right? So we can start imagining problems that might stem from that. So what kind of problem? So P1 is trying to use the resource, and P2 wants to use the resource. What would happen here? Or even better, let's start with a different scenario here. Let's imagine that P1 wants to use resource 1, which is the printer, and it wants to use the scanner, which is resource 2. And P2 wants to use the scanner, so resource 2, and it wants also to use the printer. What might happen here in that particular case? Let's see if we're using the tick, time slicing that we talked about earlier. So P1 will get its hand on R1, right? So it has it now. And then time slicing will go to P2. P2 will execute, will try to take R2, which is still free, will take it, and then time slice up, we're back to P1. P1 will try to take R2, however R2 this time is taken by P2, and it didn't let go of it still. So basically I got blocked. So I'm back to P2, and P2 is trying to take R1, which is taken by P1, and it didn't, let it go still. So I'm gonna get blocked as well. So you can notice that no one is able to move anywhere anymore. And this is, you can read that later. This is what we call a deadlock, and this is an analogy. You can read it later. Have fun with it. So a deadlock means that no process is able to move forward because each resource is being taken by in each process, and no one will let go. Another problem might be, like poor Homer here, is even if P1 got to take R1, for instance, fair enough, and P2 is trying to take R1. However, for some reason, P1 has a infinite while loop in it, perpetual one, and then never letting go of R1. So the poor P2 will never be able to take R1. So this is what we call starvation. Let me take out that. So when the process is indefinitely denied access to a resource, this is what we call starvation. And we just imagine a scenario when we have starvation, and it's the simply P1 get its hands on R1 on the printer, and it's printing forever and ever and ever. Alright, so we've seen the hardware resources, and then in class we try to imagine a different type of resources, and in this case we wanted to tackle software resources. So I asked people if you already dealt with global variables and local variables, so you already did, so I'm not going to explain it. So we're supposing that we have two processes here, and those processes are sharing x and y. So x and y are global variables for everyone, right? Visible from anywhere. And P1 and P2, they are sharing those variables. So when we say we are sharing something systematically, now we're going to think that it's a critical resource. And let's see what would happen here. So let's imagine that the critical section that is responsible for the critical resource here we started with P1, assuming that x is equal to 0 at the very beginning. This is its init value, initial value. So x would be equal to 1 at the end of that instruction, and then y would be equal to 2 at the end of the instruction. However, if we're doing something like that, so P1 will execute first, we will execute the very first instruction here, so x from 0, it will be equal to 1 now, and instead of continuing with y here, well, we got preempted and P2 executed. So x is incremented again, so it went from 1 to 2, and then we got preempted, we're back to here, and y would be equal to 2 plus 1, 3. But that's weird, because we wanted x to be equal to 2, but now we ended up with x equal to 3. So this is another reason, because it's a critical resource, we need to make sure that if I'm entering this critical section, P2 should not be able to execute its critical section. Fair enough? So we're gonna try and protect that. Alright, so you can notice that they're competing over the different resources, and this could change the data coherence. We'll have a problem here. The problematic is data coherence, because if P1 executes normally, we're gonna end up with y equal 2, but if we don't protect well, we're gonna end up with y equal 3. Alright, so the mechanisms that are already provided by the kernels, by the normal kernels out there, are called semaphores, and we're gonna see 3 types of them today. Alright, and we're gonna see which one is the most suitable for mutual, to enforce mutual exclusion. The fact that if someone's using something, and no one else should be able to use it. Alright, so semaphores, we can see it as a integer value that is used to signal among processes. Alright, I'm gonna start with the first type, so I need to explain what I mean by that, and then we're gonna get to the different types. So imagine that I have a bunch of stalls, toilet stalls, like 5 toilet stalls. Alright, and each and every time a stall is available, well, I have a key for it. So 1 key per stall. So if we're having 5 stalls, well, we'll end up having 5 keys. So each and every time a process wants to use a stall, so a stall in this case is a resource, right? We're gonna take out a key. So we go from 5 to 4, and then if you have P2 here, it will be 3, P3, etc., etc. Right? So we're keeping track of the available resources using this first type of semaphores. So how would you engineer that one? Pause the video, think about it, and then resume it. So to engineer it, well, easy. We need something to increment and decrement, plus it should have an initial value. So basically, this is nothing but a integer value where we can initialize with the number of keys at the beginning, decrement, and this is what we're gonna call technically from num some weight, right? So we're gonna go check. So I'll need to use a resource. Let's see P4. So before using the resource, I need to check if there are available keys. All right. If there are not available keys, I'm gonna get blocked. If there are available at least one available key, I'll be able to proceed. Right. So this is the sum weight, and then I can sum post, which is increment. So once I'm done, well, I can increment the number of keys. And it may result in right. So this is wrong. This should be called aka take. We're trying to take a semaphore. Voila. Right. So how to manage block processes, and which is true about processes is also true about threads. So the idea is it's either the first one to ask for a key will be the first one to be unblocked, for instance, once a key is available, or if I'm not using that one, it could be based on the priority. It could be anything. really. Alright, so this is exactly what I told you about. You can read it on your own. So all we have to do is check the number of keys. If it's available, well, this is what we're gonna do. Well, if we don't have any more keys, well, it will be unavailable. But what I need you to notice here is that any process can increment or decrement a semaphore. And this first of type of semaphore, we're gonna call them counting semaphores, alright? Because we have multiple keys. We could have multiple keys. So any process means that even if I don't own the key, because after all it's just a variable, right? So someone can increment it or decrement it. So even if I'm not the one who decremented the variable, I would be able to increment it. This is its nature. This is what we call counting semaphore. Alright, so the question is, are counting semaphore appropriate for enforcing mutual exclusion? Well, the answer is not, because any process can increment or decrement. Plus, we can have multiple keys, so it doesn't make any sense. We cannot guarantee that only one inside the resource. We just can keep track of how many resources are available. So this is the purpose of counting semaphores. Now let's see, instead of having multiple resources, let's imagine that we only have one resource. So my counting semaphore, instead of really counting, well, it's not counting anymore. It will be either the resource is there, available, or not available. So as if I had only one key. It's either there or not there. So instead of calling them counting semaphores, let's call them binary semaphores. Fair enough? So is this type of processes of mechanisms, or semaphores, more appropriate for mutual exclusion? Let's see. So if this task is trying to access the printer, well, I'm gonna go check if the key is available. If the key is available, well, I won't be able to. If it's available, I will be able to print it. If not, well, I need to wait for it to become available. Maybe task number 2 is using it. So this one is way better to enforce mutual exclusion. However, there's still a problem with it. What is the problem? Same warning here. The caveat here is that still any process can increment or decrement it. So let's see a scenario. Why is it dangerous? Maybe someone, remember, a process is nothing but a program with a PCB and it's active, loaded in memory and trying to execute, right? So maybe someone in their program tried to do something like that. Instead of waiting for the semaphore, systematically I'm gonna go ahead and post, right? I'm gonna, even if someone has already taken the key, I'm gonna increment the key as if it's available now and go and print out, and we're gonna end up with the messed up gibberish that we had earlier. So still, it's better than the counting semaphore for mutual exclusion, but it's not the thing that I want to use for mutual exclusion. So this one is also a signaling mechanism, however, it's only for one resource. So it's nothing but a counting semaphore with only one key. Alright, so let's see a scenario. So one group, face-to-face group, we've done the scenario, and the other face-to-face group, we play the game. So I'm not going to play the game using on the video, it wouldn't make any sense. But I'm gonna explain the scenario here. Laser pointer. So apparently we have one processor here. We have a bunch of processes that are ready. So apparently, if we look at it, the selection from the ready queue is based on a priority no, time slicing no. Feels like it's a first in, first out, and it is first in, first out. So let's see, we have a semaphore here, and using a counting semaphore. This is the type of it. 4 processes, A, B, C, and D, they want to take the semaphore, and D just want to post semaphores. We good? So D will increment the key and those will decrement it. So let's go for it. So here we have a key. A has entered the processor, is trying to take the semaphore. We have one available key, so I'm not gonna get blocked. I'm gonna be over, keep the thingy, and back to the ready queue. Now it's B's turn, so B is here. B is trying to take the semaphore. Whoops, no keys are available, so I'm gonna get blocked. Right? Now the negative numbers here means how many processes are being blocked over the semaphore. Fair enough? So we're keeping track of how many processes are being blocked. Right? The positive number means how many keys are available. Alright, so D is back. Check this out. D will increment. So systematically D incremented the semaphore. We went to 0 and we unblocked. So we created the key, been taken by B. So B got unblocked, executed, and then went back to the ready queue. It didn't give it back. It doesn't give it back. So the only one that gives back keys is D. Now it's C's turn. So C is here. We have 0. Whoops. We're gonna get blocked. Followed by A. A is going to try to take the semaphore. Whoops. We had a -1 here. So we're gonna get blocked. Same Z's for B. And we're gonna end up with -3 here. So 3 processes attempted to take a semaphore that is not available, and we ended up with 3 processes waiting for it. Hence the -3 here. So D is back. D will increment the semaphore, the counting semaphore. So we're gonna unblock one of them. So the first one to unblock is the first one to ask for it. So it is C. So C will be able to execute. And we still need D to execute 2 more in order to unblock everyone here. What if D does not execute but C is executing again? And this is the case because remember, so those 2 will never be able to get unblocked because we'll always be blocking, unblocking. We won't be able to unblock everyone until D is the one that is executed many times. So you can try to imagine a continuation for this scenario. What would happen here? So D executed, it will be back here. C will try to execute, it will be here. So then A, when D will execute one more time, will be unblocked, and you can see that we will always end up with 2 blocked processes. We good? Now remember that when I told you that counting semaphores and binary semaphores are good to keep track of available resources, but they're not good to enforce mutual exclusion. So the idea, in order to enforce mutual exclusion, well, pause the video and think about should we transform the binary semaphore in a way that will be able to enforce mutual exclusion. Well, the answer here is easy. The problem with the binary semaphore as the counting semaphore, but I care about the binary because it's only one key. Right? So with the binary semaphore, anyone can increment. Anyone can give back a key even though it doesn't own it. So the idea is, all you have to do is add another constraint is, and that would be the process that has the key is the only process that is allowed to give it back. Right? So if P1 is the one that decremented, that taken the key, P1 should be the only one that is allowed to give it back. Even if P2 tries to do so, we won't be able to do that. We need to enforce that. Right? So this is where mutex is becomes handy and is the third type of semaphores we're seeing. So it's a binary semaphore with one key. However, the process that locks is the one that unlocks. Alright, this is an additional constraint. Hence, we can force mutual exclusion. And you can notice from its name, mutex stands for mutual exclusion. So it was created for that particular reason. Alright, so go ahead and play your game on your own. Try to guess those and then get the answer from the slides. Alright, so here again you can try and guess the different elements. So this is a new one, and this is I didn't talk about, but it's so obvious. And those we've covered them. Alright, so have a nice one and hope to see you face to face really soon.